Hello everyone, welcome to the next lecture on the real analysis. Today I will explain you how you can solve or how you can discuss about the uniform convergence of the series of function. Myself Dr. Harish Garg. You can follow my YouTube channel where you can find the playlist of the real analysis. We have seen that in our previous lecture we have defined, explained, complete about the sequences of the function. You can see the various lecture available. Also I have explained you the concept of the CSR net examination problems with the help of the shortcut tricks. Apart from them, we have defined the series of the function as a pointwise and the Cauchy criteria. So as I mentioned you, we have discussed the sequences of the functions and we have covered all these points in our last lectures. In this lecture, we will define the concept of the series of the functions and try to understand the concept of all these properties with the help of series of the function. Now, what we have discussed so far, we have covered the first concept, that is a pointwise convergence of the series of the function, and that lecture you can see in my playlist, pointwise convergence series of the function. Now, in this lecture we will define some more stronger condition of the convergence, that is called as the uniform convergence. How you can define the uniform convergence, how you can solve the problem, and what is the concept behind that, we will see in this lecture. I hope you can like and comment on this video as well. You can share this video with your other friends and the students too. Whenever you have a subset A of the R and we can define the infinite series summation of UN, then whenever you are defining the series of the uniform convergence, your first target is to define the nth partial sum sequence. What is the meaning of the nth partial sum sequence? We can define this infinite series from n is equal to 1 to infinity to the nth partial sum sequence as u1x, u2x and unx. Remember students, fnx is my sequences of the function. Fine. And once we know this is a sequence of the function, based on all our previous lecture, we can define the convergence of the infinite series. When the infinite series is said to be the pointwise convergent, when this fnx, that is the nth partial sum sequence, converges to the fx pointwise. Secondly, when this sequence fnx converges to the fx uniformly. And then you can say the series also converges to the pointwise, series also converges uniformly. And we all knows how you can check about the pointwise convergence. We can find the limit as n approaches infinity. If this limit is my unique and existence, we can say it's my pointwise convergence. Now, how you can check about the uniform convergence? Remember student, whenever there is a question related to examine the uniform convergence of the series, check whether the series is uniform convergence, test whether the series is uniform convergent or not. Your first target is always to examine these 2 points, pointwise convergent and the uniform convergent. Fine. So how you can check about the pointwise and uniform? We firstly define the sequences called as the nth partial sum sequence, and then we can define the pointwise convergence like limit as n approaches infinity. If this limit exists and unique, remember uniqueness is also the most important, then you can say the fnx converges to the f pointwise. This implies the series unx converges to the fx pointwise. Fine. On the other hand, if my limit does not exist, limit does not unique, then we can say the series or the sequence does not converges to the pointwise. Fine. Second, for more detail, you can watch about my this pointwise convergent. Now, how you can check about the uniform convergence? There are the 2 methods I will explain you. The first method is by using the definitions. Second method is by using the WM test. In this lecture, I will explain you how you can check about the uniform convergence by using the concept of the definitions. What is the definition is? That is a fnx minus fx should be less than epsilon. One most important thing is, because student, we all knows this is my sequences of the function. Fine. And our previous lecture we have already defined how you can check about the sequences of the function as a uniform convergence by using the MN test or by using the definitions. So we will apply the same concept and the same way we can solve in this lecture too. I will explain you the 3-step rule how you can solve the uniform convergence of the series. The step number 1 is we can define the nth partial sum sequence, that is u1x plus u2x plus unx. Second is we can check about the pointwise convergent. How we can check about the pointwise convergent? We can compute the limit of the fnx as n approaches infinity. If this limit exists and this limit is my unique, then we can say this function fnx converges to the fx pointwise and the series converges pointwise. And the last way is you can define the fnx minus fx. Because remember again, this is my sequence. For more detail about that, you can watch about my this lecture on the sequences of the function. I will use the same way you can solve in this lecture too. Don't forget to subscribe my YouTube channel. I will explain you with the help of the numerical examples. Discuss or show the series converges uniformly on the closed interval 0, 1. Now first of all, this is the series. So clearly say this is my u1, this is my u2 and this is my un. So I can write this term is my un. Can you write this quantity as a partial fraction? I can quickly recall you how you can write the partial fraction. If I have the term, for example, this, how you can write this as a partial fraction? I can write this number is x plus 1 and x plus 2. I can substitute this denominator as a 0. The value of the x is minus 1. I can substitute x is equal to minus 1 everywhere apart from this term. So the value will be minus 1 plus 3 divided by minus 1 plus 2. The answer is 2. Similarly, for this case, I can substitute x is equal to minus of 2. I can substitute everywhere apart from this term. So minus of 2 plus 3, minus of 2 plus 1. Answer is minus 1. So this is the partial fraction. By the same way, I can define the partial fraction of this expression plus x plus n. So I can substitute x is equal to 1 minus n, because if I substitute 0, I can substitute x is equal to 1 minus n in this expression. It is minus 1. So n will be cancelled out. Answer is minus 1. From this case, I can substitute x is equal to minus n apart from this quantity. So it's a minus 1 n. So it will be plus 1. So the partial fraction is minus 1 and the plus 1. Fine. Now we can define the step number 1. We can define the fnx, which is defined as u1 plus u2 plus u3. u1 is my 1 over x plus 1. u2, because n is start from the greater than equal to 2. Fine. Because if you consider here is n is equal to 1, then it is my x into x plus 1. But the first term is only x plus 1. I can substitute x equal to 2 here. This value will be minus 1 over x plus 1 plus x plus 2. Similarly, you can substitute x3 and the last term is n. Clearly say the first value will be cancelled out, the second value will be cancelled out, and the only term which is left behind is 1 over x plus n. Fine. Now we have defined the sequences. Then we can check about the pointwise convergent. So can you take on the limit? Limit as n approaches infinity of fnx. Fine. Now since my function is the closed interval, I can consider the 3 cases. Firstly, x is my 0. Second, x is equal to 1. And the third case is x lies between 0 and 1. What will happen if x is equal to 0? Then fns will be 1 over n, then the limit will be 0. If x is equal to 1, your fnx will be 1 over 1 plus n. Again, if you consider the limit, it is my 0. And if x is lies between 0 and 1, again if you consider the limit as n approaches infinity, the answer is 0. So therefore, you can say fnx will be 0 for all x here. And you can see the limit is unique and existence. Therefore, the nth term sequence converges pointwise. That means the series converges to the f pointwise. What is the f is? F is my 0 on the closed interval 0 comma 1. Now for the second case, that is we need to check about the uniform convergence, we can start with the fnx minus. So what is the value of the fnx minus fx? Absolute value. What is the value of the fnx? Is a x 1 over. What is the value of the fx? Is a 0 for all x. So the answer is 1 over x plus n. Fine. Now I can substitute this 1 over n plus in here. So I can assume let epsilon is a greater than 0 be the given number such that this quantity hold. That means 1 over x plus n is less than epsilon. Your target is to find the value of the n. So can you find the value of the n? So x plus n is greater than of the 1 over epsilon. N is greater than of 1 over epsilon minus x. Fine. Every time you need to find the value of the n. Then always there are the two cases. Case 1, can you find the value of the x? Can you find the value of the x from the domain so that the value of the n, that is this expression, will goes to the infinity? Fine. In this case, there is not possible. Fine. Second case, if it is not possible, then your target is to find the maximum value of this expression. Your target is to find the maximum value of this expression. Clearly say in this particular example, this case is not possible. Fine. Because if I say my expression becomes 1 over x, then clearly say if I choose x is my 0, then this expression becomes my infinity. Fine. Or minus infinity. So now in this case, our target is to find the maximum value of this expression. How you can find the maximum value of this? Because of this negative number, the maximum value of this is equivalent to the minimum value of my x. So what is the minimum value of the x? 0. So therefore, the maximum value of the x is 1 over epsilon minus 0. That is 1 over epsilon. Fine. So this is my maximum value. So I can choose a positive integer m, so that m must be greater than of 1 over epsilon. And because 1 over epsilon is the maximum value of 1 over epsilon minus x. So therefore, our target is fnx minus fx is less than epsilon whenever n is greater than of this number. So therefore, fnx converges to the f uniformly over the closed interval 0 comma 1. Hence, the series converges uniformly over the closed interval 0 comma 1. This is the first example. Look at the second example. This is the expression of my u1. This is the second term. This is my u2 and this is my un. So I can write the first quantity as a un. Now clearly say there is no need to do the partial fraction because it is already happened that. Now I can define the step number 1. We can define the fnx, which is defined as u1 plus u2 plus un. What is the u1? This is x square over 1 plus x square. 1 minus 1 is a 0. u2, when you substitute n is equal to 2, is a 2x square over 1 plus 2x minus x square over 1 plus x. This number is my 1 plus x only, and so on. Fine. Now can you do that? This value will be cancelled out. Second value will be cancelled out. This value will be cancelled with the previous term. The only expression is my nx square over 1 plus nx. Once you define the fnx, then your target is to check the pointwise convergent. So your target is to compute this limit. Again, you can see that it's a closed interval. I consider the three cases. X is equal to 0, x is equal to 1, x is lies between 0 and 1. If x is equal to 0, what is my fnx is 0. The limit is also 0. If x is equal to 1, what is my fnx? If x is equal to 1, the limit will be n over 1 plus n. Now if you take the limit as n approaches infinity, this is my infinity by infinity form. I can apply the L'Hopital rule. It's a 1 over 1. Answer is 1. And whenever x lies between 0 and 1, we can find the limit of n x square over 1 plus nx as n approaches infinity. So clearly say it is a infinity by infinity form. I can apply the L'Hopital rule with respect to the n. So the derivative of the n is x square, derivative is my x. So 1x will be cancelled out, so the limit is my x. Now clearly say in all the cases, the limits are my the limits are existence and also uniqueness. So therefore, you can say the sequences of the function converges pointwise, hence the series converges pointwise. Now, how you can check about the uniform convergence? We have the two methods. I will explain you this example by the both way. I will firstly explain you with the help of the first method. Again, your target is to compute fnx minus fx. Now clearly say you have the three different cases. The first case, when x is equal to 0. What is the value of the fnx? Fn is my 0, f is my 0. So this number is my 0. Second case, when fnx minus fx, when x is equal to 1, your fn will be n over 1 plus n, and when x is equal to 1, fn is my 1. So if you subtract them, answer will be minus 1 over 1 plus n. That will be 1 over 1 plus n. And similarly for the third case, your answer will be nx square over 1 plus nx minus x. If you LCM them, it's a minus x over 1 plus nx. So clearly say this is a particular case of this by taking x is equal to 1. So your fnx will be x over 1 plus nx. Now your target is to find the supremum. I can substitute this value in the given function. So your mn will be supremum of this. How you can find the supremum? There are the two ways. Firstly, you can take y is equal to x over 1 plus nx. Find the first derivative to be the 0. Find the value of the x from this case, and second derivative to be less than 0. This is the first method. Otherwise, the second method is you can choose about the domain. Because my domain is 0, 1. Fine. You can choose any value of the x in between them. Either you can choose 1 minus 1 over n, or you can choose any of the sequence as 1 over n and so on. That's on your choice. Fine. So the easiest way is I can choose the subsequence as 1 over n. I can substitute this value in the given mn. Remember, your target in this mn is it should goes to the 0 in order to for the uniform convergence. So mn will be supremum x over 1 plus 1. So that will be 1 over 2n. Fine. So what will happen as n approaches infinity? So clearly say this will goes to the 0 as n approaches infinity. So therefore, by mn test, the sequences of the function fn converges uniformly to the f. Hence the series also converges uniformly. Second method is, again by using the definitions, I can find the value of the fnx minus fx. Fine. Again, either you can take it as a equality or you can take it as a separate. There is no issue, because for the first case you will get this value when x is equal to 1, and whenever x is lies between 0 and 1, you will get the answer as, and you can see that this is my particular case of this expression. Fine. I can substitute this value in the given point, and your target is to find the value of the n. So how you can find the value of the n? I can cross multiply them. It's a n epsilon into x. So can you find the value of the n? That is x minus epsilon. So your x minus epsilon divided by x into epsilon is my n. So that means n is greater than of 1 over epsilon minus 1 over x. Fine. Again, you have the two different cases. You have to find the value of the x from the given domain. What is my domain in the given statement? Domain is 0, 1. So that so that n will goes to the infinity. Second is your target is to find the maximum value of this expression. Expression is 1 over epsilon minus 1 over x. Now, can you find the maximum value of this firstly? How you can find the max? Because of this negative, our target is to find the minimum value of the 1 over x. Again, when it will be the minimum? When the denominator is my maximum. So what is the maximum value of x is 1. So therefore, the maximum value is my epsilon 1 over epsilon minus 1. I can choose a positive number m so that m will be greater than of this, and because this number is my maximum value of this expression. Fine. Now you can say the sequences converges to the Fn. Fine. Hence Fn series is also converges Fn. Also remember, if you think about that, can you find the value of the x? Can you find the value of x so that n will goes to the infinity? If you choose x is equal to 0, then n will goes to the minus of infinity, but we need as the plus infinity. So there is no value of the n we can obtain. Okay, look at this another case. Show that the 0 is the point of non-uniform convergence. Again, this is my u1, this is my u2, this is my u3. Can you define the nth term? Is x square 1 plus x square raised to power 1 to n minus 1. Then, because there is no need of the partial fraction, I can use as the nth partial sum sequence. Now I can substitute the value of the u1, u2 and un. What is the value of the u1 is x square, because 1 minus 1 is 0. u2 x square over 1 plus x square and so on. The last expression is x square over 1 plus x square raised to power n minus 1. Now can you find the sum of this? Clearly say this is the GP, and the sum of the GP series up to the n term is a 1 minus r over 1 minus r. So a will be my first term. What is the common ratio? Common ratio is 1 over 1 plus x square. So I can substitute this value a 1 minus r raised to power n. How many terms? There is n terms divided by 1 minus r. Fine. Now if you take the LCM, clearly say 1 will be cancelled, x square will be cancelled. The expression becomes my 1 plus x square into 1 minus 1 plus x square raised to power n. Fine. So this is the expression of this Fnx. Dear student, I hope you can like and comment on this video as well. Now once you can define the Fn, we can define the pointwise. We can take the limit as n approaches infinity. Now you can see that in this case there is no closed interval is given to you. Then we can consider the two cases. The first case is, first of all, you can see this number can never be 0. So I can say either x is 0 or x is my non-zero. What will happen if x is equal to 0? Your Fnx will be 1, 1 minus 1, that is my 0. So this answer is 0. And if x is my non-zero, then what is the limit is? Limit n approaches infinity 1 plus x square of 1 over 1 plus x square. Now since my limit is with respect to n, 1 plus x square is outside. This is my 1. What is this limit? Clearly say whenever x is my non-zero, 1 over 1 plus x square always lies between 0 and 1. Fine. And any number which you raise to the power n, if it is a 0 and 1, it goes to the 0 as n approaches infinity. So the answer is 1 plus x square. Fine. Now clearly say both the limits are existence. Therefore the series as well as the sequences Fn converges pointwise to the F. Now we can define the nth partial sum sequence. We can define the uniform convergence. Let's define the Fnx minus Fx. Again, you have the two cases. If x is equal to 0, what is the value of the Fn? Fn is my also 0. Then 0 minus 0 is 0. On the second case, Fnx minus Fx. If x is my non-zero, this is the case when x is equal to 0. This is the case when x is my non-zero. So I can substitute this value. I can open that. It's a 1 plus x square minus, it is 1 plus x square raised to power 1 minus n minus fx. Fx is my 1 plus x square. So 1 plus x square will be cancelled and I can take on this modulus value as a positive number. Fine. Then I can substitute this value in the given expression and your target is to find the value of n. How you can find the value of n? I can firstly take the reciprocal. It is greater than of 1 over epsilon. I can take on the logarithm on the both side. So then n minus 1 should be greater than of log 1 over epsilon divided by log of 1 plus x square. Fine. And then the value of n is 1 plus of this. Again, your target, can you find the value of the x from the domain? In this case, the domain is my real line. Can you find the value of the x so that n goes to the infinity? Yes, clearly say if I choose x is equal to 0, then the value of the n will goes to the infinity because log 1 is 0 and it's a positive. So therefore, you can say 1 over, that is a log 1 over epsilon, this value goes to the infinity as x approaches 0. So then this x is equal to 0 is named as non-uniform point of convergence. Fine. So therefore we can never choose a positive integer n which satisfies this condition, implies fn is not uniform convergent on any interval which contains my 0, whether the interval is -1, 1, whether the interval is -3, 7, whether the interval is -3, 100, or whether it's a r. So this sequence or this series is not uniform convergent on any interval which containing the point 0, and that point 0 is called as the non-uniform convergence. And clearly say if you have the interval, if you have the interval is say 2, 4, so clearly say 0 does not belong to this, and then in that case it can never goes to the infinity. So therefore it is a uniform convergent. But because in this particular example the range or the domain is given as a real line, so therefore we can say this series is not uniform convergent on any interval which containing the point 0. And this is the way you can check about the non-uniform convergent. We will see the next lecture, which is more than 10 examples again on the uniform convergence in our next lecture. Till then, you can like, subscribe and comment on this video, and don't forget to share this video with your friends. I hope you can subscribe my YouTube channels, and thanks for the watching. Thanks for the support. Happy learning, students. Best wishes.